Creating Other Schema Objects Part 2 of 2. In this nugget we turn our attention to two additional types of objects that you're likely to see each day as a working Oracle Database Administrator. The first of these are indexes. Indexes are used to dramatically improve the performance of some queries. Now notice I said some. One of the objectives for this nugget is to teach you not only what indexes are and how to create them, but also when to create them and when not to create them. That's an important fine-tuned skill. The second part of this nugget considers synonyms, which represent alias names for database objects. This can make it a lot easier for users to refer to objects in their queries without having to use fully qualified syntax. Let's get to work. What are indexes anyway? Indexes in relational database systems, as I just said, are schema objects that are used to speed up data retrieval. Analogously, you can open up a textbook and go to the back of that textbook to find an alphabetized index of topics. So if we, for instance, were reading a book on chemistry and we wanted to learn about, let's say, chemical formulas, we could open up the index, go to the F's, look up the word formula, and then we'll see lookup pointers to pages in that textbook that reference that concept. Same basic idea here with database tables. Thus far, we've been taking it for granted that when we run a select statement, in particular more complex select statements that filter rows using where and involve different kinds of joins, that Oracle just knows where to find those rows. We've kind of abstracted what's going on under the hood. Well, indexes are crucial, as I said, because as you're about to see when we learn about the two specific types of indexes covered on the exam objectives, that when Oracle uses an index, you'll see dramatically increased performance. One reason for this increase in performance in index usage is that indexes can drastically reduce disk I/O. Of course, we know that fundamentally your table data are stored in Oracle data files that exist on one or more physical hard disks on your Oracle server, or potentially even outside the Oracle server on other disk appliances. Now we get into the where-bys and heretofores and where to place your data files in my other CBT Nuggets course on the DBA1 objectives. Here, of course, we're dealing strictly with SQL, but know that it's recommended as a best practice to place your Oracle table data files and their associated indexes on separate hard disks. The reason for this is what's called parallel processing. We could have Oracle manipulating table rows, satisfying queries for some users over here on this disk, while at the same time performing index scans and index seeks on a separate disk. So that differential disk situation can definitely help. And also you're reducing disk I/O when you're using indexes because Oracle isn't scanning every row of potentially huge tables in your database. Instead, it's skipping through what's called the balanced tree, or B tree, that comprises the vast majority of your indexes. We want to avoid what are called table scans at all costs. As it happens, and here's a point of vocabulary for your consideration, any relational database table that does not currently have an index on it is stored as what's called a heap, kind of a funny word. And any selects that go against a heap table are always going to result in the Oracle Query Optimizer performing what's called a table scan. Now this is going to be the most expensive operation CPU-wise, memory-wise, disk I/O-wise, and network-wise, because in order to pull those rows, Oracle is going to have to check each and every row in its entirety in that table. Now in some cases heap tables are alright. If you know you're going to select star or select all rows and all columns, then there's really no need for an index there. But by and large, the purpose of relational database systems is to break out your table data so granularly that you can use joins and very selective select statements to pull only particular rows from those tables, in which case an index would be essentially mandatory. Now in the SQL Fundamentals exam objectives, we're not concerned with SQL optimization as such and index maintenance. Again, we cover a lot of that subject matter in the DBA1 course. Just know that Oracle does quite a bit of self-tuning. It is possible to reorganize and rebuild indexes, but some Oracle DBAs don't believe in that because they believe that Oracle 11g self-tunes its data storage to the point where that index maintenance is largely irrelevant. that's an argument for another time. The final point on this whiteboard is that although indexes are separate schema objects and they're maintained separately from tables, that is to say, you build a table with create table, you build an index on that table with create index. If you do drop the table, Oracle will automatically and transparently drop its associated indexes. Just keep that in mind. Makes sense, because why in the world would you want to have invalid indexes in your database schema? I alluded a couple minutes ago that there are two chief index types in Oracle. One is the B-tree or the balance tree. The other is the bitmap index. B-tree is going to be where it's at as far as 99% of your index use. So it's important for us to understand this concept. It's really not all that complicated. B stands for either binary or balanced. In the Oracle documentation, they call it balanced tree, so that's what we'll do right here. And I'm going to set the stage by using an analogy to a pharmacy. I used to work at a pharmacy earlier in my life, so I have some personal experience with this. Now, if I were a pharmacy clerk and working with the public to give them their prescription orders, accept cash, etc., imagine how it would be is if I went up to my counter and said, okay, hello, may I help you? And they said 2 prescriptions for, let's say, Davis, last name Davis. And I turned, and instead of seeing a nicely organized matrix of buckets containing prescriptions alphabetized by, say, last name, we had all of the store's completed prescriptions in a single box, just hither and yon, just a stack of prescription bags. Imagine what that would be for me to, for each customer, let's say there's a customer named Smith who just showed up, another one called Walker. I would need to go to that big box, look through every bag to find the one that I need. That's not very efficient, is it? This is akin to the table scan operation in a relational database management system. And it's also akin somewhat to a heaped table, a table without an index. Now then, the way pharmacies work, at least in the States, is that we have a matrix, a shelf system, where typically prescriptions are organized by last name. Maybe you have A, B, C, D, etc. I'm not going to continue this, but you've got a bucket or a compartment for each letter of the alphabet, and maybe within that bucket, it's further subdivided, DA through DB, DC through D's G, you know what I'm saying? That way. Now, the reason why this is more efficient, of course, is that if I'm looking up prescriptions for Davis, I can ignore just about all of this matrix and instead focus specifically on the drawer that contains last name D. This procedure is going to dramatically improve my times as far as satisfying those prescriptions for those customers, isn't it? Because we're able to drill directly into the area of interest. All right, transitioning this over into the balanced tree or B-tree setup for relational database systems, what you have is a collection of data pages, data blocks actually in Oracle terminology, that in a sense split your data set in halves or in equal chunks, such that in this example, let's say we had a table for employees and we created this B-tree index on the key field, let's say employee ID field. The first layer of the B-tree, these blocks are called root blocks, and they perform the initial division, and Oracle decides what that division is. In this case, let's say there are 100 rows in that employee's table. The root block division would be 1 through 50 on the left, 51 through 100 on the right, and I'm using left and right here just for the purposes of this example. I'm sure you know that. Once we start binarily or in a balanced fashion subdividing into additional data blocks, you get to the second layer. These are what Oracle calls branch blocks. These don't contain any data other than the key values. They're meant to further narrow down your result sets. So on the left here you have 1 through 25, 26 through 50, 51 through 100, you have 51 through 75, and so forth. Now how many layers Oracle uses in its branch blocks is up to it. But ultimately you come down to the leaf level, and the leaf level contains not only your key value, in this case employee ID, but also one or more other columns depending upon specifically how you set up that index. Now traditionally you'll have what's called a row ID, and this is a pointer to a location in the table's data file where Oracle can find that row. So if we were doing a query where we were gathering in our where clause employee IDs 1, 2, and 3, notice how fast this is doing an index seek, as it's called, because we can immediately discount half of the record set, focus strictly in here, and skip down through those branch blocks, again ignoring any that are irrelevant relevant and quickly come to the row IDs that we're looking for. And typically, if we wanted other columns, let's say we wanted to select employee ID, first name, last name, we would need to make use of these pointer references to quickly find that data in the source table, and then Oracle returns the query results. It's not any more complicated than that. And if you understand what I just taught you, you understand the vast majority of what there is to know about the operations of most indexes, not only in Oracle database, but any relational database system. Now, how are indexes created in Oracle Database 11g? Two ways. You can either have Oracle automatically create the index, actually it's going to happen whether you want it to or not, or you can manually create the index. An index is created using standard DDL syntax. You have create, alter, and drop, just like we've had for tables and other objects we've looked at so far. And as you also know, we can do it using old-fashioned SQL, or we can use graphical tools, for instance, in Oracle's SQL Developer utility. Now, what about this automatic thing? Let's look at this a little more detail. I mentioned that Oracle will create an index under certain cases automatically. Specifically, when you apply the primary key constraint or the unique constraint to a column in your table, Oracle will deploy an index in those cases automatically. You can then use alter index if you want to rename or change the properties of the index, but Oracle will create them. That's pretty standard really for most relational database platforms. That's not specific to Oracle. Now, the reason why Oracle deploys an index is because it assumes that if you're marking a primary key constraint on a column, then that's going to be a frequently used field in queries, if for no other reason, when you're doing compound selects that involve table joins. As you know, primary key has an analog. In the related table, there's the foreign key constraint, and that's actually a planning point for you as database architects. Oftentimes, a database developer will index on a foreign key column as well. In other words, create another index that indexes or keys on the foreign key to improve the join performance in those complex queries. Essentially, guiding principles in terms of creating index is you need to really analyze and get a handle on the kinds of queries that your users need to perform on your data, and let that be your guide. Now, no, I haven't mentioned this explicitly yet, so I'll just tell you now, know that you can in fact apply more than one index per table. There's no rule in Oracle by any means that there's a one-to-one relationship between tables and indexes. You may very well have cases to create more than one index. In a sense, I like to look at deploying indexes as giving Oracle some additional blueprints to work with, such that when queries are issued against those objects, Oracle, if there is an index available, or even more than one index available, Oracle can, in its infinite wisdom, formulate the best query execution plan by selecting the best index for the job. Now, that having been said, you don't want to over-index. The more you index, the more overhead there is in data storage, and the more overhead there is just with processor, disk I/O, etc. So I guess B-tree, balanced tree, can apply not only to the operation of most indexes, but also in how you should approach creating the indexes in the first place. Another point to consider are that of composite indexes. A composite index is an index that's created on more than one key column. And the thing to remember, the question here is cardinality. Now, as you know, the way the balanced tree works is you split down and down and down, and eventually you get your key column values and then row IDs to where you can find the rest of the data in the source table for those rows. Now, if all the select wanted to return were those key values, then the Oracle can satisfy the query entirely in the index, can it? Other than that, if you wanted any other columns, you'd have to use the row ID pointers. When you create a composite index, you're keying on more than one value. I'll just say X, Y, Z, A. And this gives the index more data. It's going to be a heavier index because it has more in it. There'll also be row ID pointers to the rest of the rows. But your query, especially if you're using operations in your where clause, and, or, etc., Oracle has a better chance of returning more data, maybe both of those columns in the query. So in this case, you need to ask yourself, besides the key column, what is the other most frequently accessed column in this table? And to speed up data retrieval, maybe I'll create a composite index that's based on both of those values. Another case where you might want to consider a composite index is if you have columns with low cardinality and you want to make the index as unique as possible per row. Now, what is cardinality? Cardinality simply refers to the degree of uniqueness you have. Obviously, any unique column or column that has the primary key constraint is going to, by definition, have high cardinality. There'll be no duplication at all in that column. An example of a low cardinality column would be something like gender. Obviously, you're just going to have male, female, or maybe N for not specified, and you're going to have a lot of repetition in that column. But that having been said, you may have queries that are constantly pulling the gender column. You may want to consider building a composite index that links the repeating gender value with a non-repeating unique column or a key column. You see what I'm saying? Keep that in mind. Finally, just in passing, we'll talk a little bit about bitmap indexes. This isn't formally on the exam objectives, but it's important enough to bear a little discussion. Bitmap indexes are definitely not advisable for heavily volatile data. You don't want to create bitmap indexes for tables that are experiencing many updates, inserts, deletes, etc. But for data that's relatively stable, in particular in, say, a data warehousing environment, and or for columns that have low cardinality, like this gender example, you may get increased performance by deploying a bitmap index on those low cardinality columns. Let me jump out to Wikipedia and show you. They have a really good article on bitmap indexes. All right, this is the Wikipedia article on bitmap index. We're going to come right down to this example area where they actually use gender in this example. Now, the idea here is that we have unique identifiers for each row, the primary key field. That's all well and good. And you'll notice we also want to key on gender, which in this case, there's just the three, male, female, and unspecified, that repeat quite a bit. When you create a bitmap index, the ordering of this data is placed not by the key column that exists in the table, but Oracle will create what's called a bit array, or a sequence of binary values, 0 or 1, that map to each unique entity within that table. And it makes sense when you think that computers speak, so to speak, binary, 0 and 1, binary code, or bits. It makes sense that if we create a bit array for each unique value, Oracle should have an easier time just zipping through to determine these, rather than have to understand some numeric identifier that we've specified as a DBA. So in this case, the bit map for female is 1, 0, male is 0, 1, and unspecified is 0, 0. And again, the idea is Oracle can satisfy this kind of query really quickly using the bitmap index type. But I hope you see that if you have high cardinality, in other words, no repetition, you're going to have a different bitmap matrix for each row in that table. And you're not only not going to save any performance, but you very well may hit your server's performance negatively big time. In this demonstration, we'll have a look at indexes in Oracle Database 11g. First thing we'll do is examine some of the indexes that already exist in the HR sample schema. To analyze these in SQL Developer is pretty easy. As you see, I've connected to the HR user, and I've selected, just by way of example, the departments table. You'll know that SQL Developer gives us these tabs that enable us to analyze various aspects of the object. So the departments table we'll see right off the bat. We have department ID, department name, manager ID, and location ID. We can verify the constraints on the table by visiting the Constraints tab, and we see, sure enough, that the department ID column is marked with the primary key constraint, and we must have table relationships coming into departments on the managers and locations table here, or at least on the locations table and probably the employees table here. Let's see. Yeah, sure enough, it looks like the reference table name is employee ID from the employees table. Now, as we said, planning indexes, you're going to get an index created automatically on your PKs, your primary key constraints, and it's often a good idea to create your own indexes to key on fields that are foreign key constraints. If we go over to the Indexes tab, we see that we have the built-in PK index that was generated by Oracle itself, and we also have one created on the location column as well, and this must have been created by the Oracle employees themselves. Now, to create an index is really easy. In SQL, the syntax is about as straightforward as it possibly gets. In this example on line 8, I'm going to create an index called emp ln idx on the employees table, keyed on the last name column. That's all there is to it. You just generate a unique name for the index, specify what table the index belongs to, and then a comma-separated list of columns that are keyed on that index. Now, of course, you can throw in some extra syntax here. You can create a unique index to guarantee unique values for every row in that index, or the B tree, I should say. We can create a bitmap index. Consult the Oracle documentation for the full syntax. We're just covering the basics here. Now, before I run this SQL, let's take a look at the employees table by selecting it in the list and see what we have going on here as far as column definitions. We've seen this before. We've been using the employees table quite a bit. Actually, it might be more helpful for us to visit the constraints column. A lot going on here for sure. We have not only our EMP-ID primary key, but we have several relationships coming into this table. And in this example, let's just say that the last name column is very frequently referred to in queries. So what we'll do here is build a standard index, a standard B-tree index that keys on that value. Simple as that. Indexes show up in your indexes list. Remember that these objects you see are per connection. So in this demo you see I've created connections for two built-in users of Oracle Database 11g, the HR if you've installed the sample schemas, and then Scott, which has always been an optional schema for training and development purposes. And when we expand a connection, we see a filtered view of objects that are owned by that user. And sure enough, not only do we have tables, but we also have a node for indexes. And once I refresh this view, we'll see our new index show up. We also, of course, can revisit the source table, employees, and see the new index added here. Let's now do a little bit of testing here. We'll examine the jobs table, which right now, if we analyze it, has only one index on it on the primary key column. We have 4 columns in the jobs table. We'll run a query called select job ID and min salary from jobs where the min salary is between 5,000 and 9,000. Admittedly, we're not pulling back much rows, so it says 0 seconds. If I expand the scope that's being pulled, 1,000 and 9,000, it fetched the 16 rows in 0.016 seconds. Now again, this may not be the best example simply because there aren't all that many rows in the jobs table. But if we now create an index, I'm going to call this create index job min sal IDX on the jobs table and keyed on min salary. Let's rerun the query. I'll expand its scope a little bit, and it cut the row down to 0.031. Marginal improvement, not anything too eye-popping, but if we select the query and use explain plan, we can see that in satisfying that select statement, it is making use of the job min sal IDX column. It's looking for specific expression values, and it's doing a range scan. So it's not the very best performance we can expect, but it's better than nothing. Remember, the worst option is the table scan. Next, we have the index scan, which is what was being used here. Ideally, we want Oracle to use the index seek. Now let's turn our attention to synonyms. The word synonym means a word or phrase that means the same thing as another word or phrase. You can look at synonym and alias being, well, synonyms. And to understand why synonyms can be so helpful in Oracle Database, it's important for us to review schema organization and name resolution. To do this, let me bring up a simple Visio diagram I've constructed for this purpose. Let's say we have 2 Oracle users. We have Tony and Sarah. Now, sometimes Oracle users are referred to themselves as schemas. I've always found that very confusing. If we want to use that nomenclature, we could say that an Oracle user that has the ability to create objects is a schema. And the reason for that is when Tony creates tables, let's say Tony created a table called prod and a table called shipping, Oracle virtually partitions those objects in Tony's schema. And the name of a user's schema happens to be, coincidence or not, the name of the user, him or herself. So the fully qualified name, or let's say the globally unique name for an object in a particular Oracle database, is going to be the schema name dot the object name. So the fully qualified name for prod is actually Tony.prod. In shipping, same thing, Tony.shipping. And that serves as a unique identifier database-wide for that object. Remember, schema refers to realm, so these objects are considered to be owned by Tony. He has full control, permission over those objects because he created them, and he can assign permissions to other users so they can access those objects. Sarah, same exact thing here. It looks like she's created two tables, one called cat and one called prod. Fully qualified names here are Sarah.cat and Sarah.prod. Now, things get interesting name resolution-wise when users start running selects against objects, or really any SQL statement, not just selects, against objects that are outside their own schema. That is to say, Tony can query his tables all day long by using either their qualified or unqualified name. That is to say, he can run select star from prod and he'll get results back all day long. Now, if he ran select star from cat, which is a table owned by Sarah, what do you think would happen? Well, two things are going to happen. One, Oracle's not going to be able to find the cat table because these schemas are essentially partitions that hide the objects from each other. That's going to be one problem. And number two, as of now, Tony doesn't have any permission against that table, you see? So number one, Sarah would need to grant Tony the appropriate privilege or privileges on the cat table to even do this select statement. So let's say, for the sake of argument, Sarah grants Tony the select privilege against the cat table, and Tony issues select star from cat. What's going to happen now? Well, although Tony has proper permissions, Oracle's still going to tell Tony that that table doesn't exist. Because again, the shroud or cloak of invisibility, as it were, that surrounds users' schemas. So Tony is actually going to have to run select star from, and then it's not Tony.cat, is it? It's Sarah.cat. As long as he qualifies the schema name to the object name, Oracle says, oh, okay, you want Sarah.cat. Let me check your permissions. Yes, you are granted select. Here are the results of the query. You see what I mean? Now, this is different from some relational database systems. There's really a hard line drawn between schemas here. Things get more interesting when you have objects with the same name. At first blush, you might have thought to yourself, how can Tony and Sarah both create a table called prod and have those tables exist or coexist peacefully in the Oracle database? The reason for that is, in fact, due to the schema name. Although the object name is the same, may even have the same types of data stored, some of the same column names, etc., they are considered completely unique and separate tables by virtue of their schema designation. So at this point, we understand about schemas, we understand about object ownership, and we understand the need to qualify names if we want to cross schema boundaries. Synonyms come in as a nice handy way to apply shorthand to reference objects in other schemas. Now let's say Tony has need for daily access to the prod table in Sarah's schema, and he's tired of, in all of his queries, referencing Sarah.prod. Well, to fix that, Sarah can create a synonym, which is just an alias name. Let's say that she created a synonym for the Sarah.prod table called PD. She could make that synonym public so Tony can use it. And now whenever Tony needs to access Sarah's prod table, he can run select star from PD. No need to do any kind of prefix of the schema name. Because the synonym is registered publicly in the database, it becomes the globally unique identifier. Or should I say it becomes a globally unique identifier for that object. It's as simple as that. You can also use synonyms to convert really wonky table names. Maybe Sarah has a table called 8675309J, if you get the pop culture reference. And to make it easier for folks to run queries against that table, she can just rename via a synonym. The table name is Jenny, and that way folks from other schemas, and even Sarah herself, can run selects against Jenny instead of having to use this cryptic table name. Alright, so back to our regularly scheduled programming. A synonym, formally defined, is an object that refers to objects in other schemas. Now, as I mentioned, there are two types or flavors of synonyms. There's private and public. A private synonym is owned by a single user and is accessible only by that user. So this allows a user to create alias names for their own objects for their own use. More common perhaps are public synonyms that can be created by any schema owner, for their objects, but the ownership of the synonym is by the public built-in group. In other words, the public synonyms are globally accessible. Now, before you think, you might be putting on your security hat and thinking, uh-oh, anything with public is bad. Not in this case. Public synonyms can be very helpful to all your users when you consider, and that's why I have the asterisk here, that synonyms are not securables. We haven't talked about security much. We're going to do a lesson on it a little bit later in this Nugget series, and we cover security in much greater depth in the DBA1 course. But a securable is an object in a database that can be secured with access control permissions. Synonyms provide no security. That is to say, remember our earlier example, let me actually bring up the whiteboard again. Unless Tony gives Sarah privileges on, let's say, his shipping table, Sarah is not going to be able to touch that table at all. Even if Tony creates a synonym to advertise the shipping table as, let's say, SH instead of shipping, Sarah can try to run select star against SH. She can try to run select against Tony.shipping, and she's not going to get anything back by way of results unless and until Tony grants Sarah the appropriate permissions. So there is a heavy distinction indeed between the synonym and security. In this demonstration, we'll examine the use of synonyms in Oracle Database 11g. Of course, you know, because I showed you in the previous demo in this nugget, we've got two connections going, two built-in users, HR and Scott. Each of these users does have the system privilege to create new objects, so officially HR and Scott are referred to as schemas. Now let's run a query into the data dictionary really quickly to set the stage. Just to remind us of the tables that are owned by each user, I'm running select table name from user tables, and I have some additional ones that you probably don't have unless you've been duplicating my demos for HR. The main ones, of course, are these 6. We'll do the same for Scott. Scott just owns 4 tables, sal grade, bonus, emp, and department. Now, we can, of course, from a user's own standpoint, their own schema, select from their own objects without qualifying the schema name. So select star from, can't leave out that important keyword, right? Works just fine. And we can also do scott.emp, not harming anything. We're going to get the same results doing that. No big deal. Just to demonstrate that that works, let me rerun my data dictionary select and then rerun select star from scott.emp. Now, HR, of course, can do that with their own tables, but what if we try to do a select star from emp? We get an Aura 942 error, table or view does not exist. Well, we know it exists because we just referenced it over here from Scott's own schema. But remember, because HR hasn't been granted any privilege on Scott's table, it's not going to work. So from HR's perspective, let's try to run a select star from Scott.emp and see what happens. Again, we get a table or view does not exist error. It isn't until we run the appropriate grant statement, which I'm going to copy from this window and paste it into Scott's window, edit, paste. We're going to grant select on emp to HR that we now can run that query all day long. Good. Now what if we wanted to give HR the ability to reference Scott.emp under a single short name? Well, that's the case for a synonym, isn't it? So why don't we, again, from Scott's view, create a public synonym, and we'll call it E1 for Scott.emp. Now in this case we got an error, an Aura 1031 error. So it seems that Scott doesn't have the ability to create a public synonym. So this failed with an Aura 1031 error, insufficient privileges. So we would have to, as the sys super user, grant Scott and HR the ability to create those synonyms, especially public synonyms that are stored in the data dictionary and available to all users. Alternatively, I have a separate connection for the sys super user. I'm just going to go ahead and create this public synonym as the super user. And of course, the sys user can do anything in the database, so that wasn't a problem. So now Scott should be able to run a select star from E1 to make use of that synonym, as should HR, because HR also has the select against that table. There it is. Synonyms in action. Finally, notice that for each connection, I guess I'll have to look under Scott here, in SQL Developer, synonyms are loaded under the synonyms folder for private synonyms, public synonyms for public synonyms. Creating other schema objects, part 2 of 2. In this nugget, we unlocked the mystery, so to speak, of indexes. We now have, I think, a pretty pretty nice wide spectrum view of the core data objects in Oracle Database, specifically the interrelationship between your base tables and any indexes that you or Oracle create for those tables. You understand what B-tree means, you know what a bitmap index is, and more importantly, you understand when to deploy each type of index in your database. We also now understand fully what synonyms are. We see that these are handy aliases for object names that can improve name resolution for our Oracle database users. I hope that this has been informative for you, and I'd like to thank you for viewing.